All right, I'm showing 1 o'clock, the top of the hour, so we'll jump on and we'll keep letting people in as they jump in. Thank you for coming to our webinar today with Nicholson. We're bringing in Conetec, one of our sister companies, to talk about cone penetrometer testing and some other recent advances in soil investigation technologies. A few ground rules before we get started. In the chat, we'll do our hellos, and if you want to tell us where you're signing in from, and then in our Q&A section, we're going to do any questions. That's where, if you throw them in the chat, we might miss them. So make sure you throw your questions in the Q&A section, and we'll be sure to have time at the end of the presentation to take some answers. If we don't get to some of the questions there, we'll try to send them out at the end in the following week. We're also recording this session. So for everybody that jumps onto this webinar, we'll be sending out the recording about a week after. And we also are able to provide a PDH for this webinar as well. So if you did not click that box to get your PDH ahead of time, when you log off of this webinar, you're going to be asked to fill out a survey. Please fill out that survey. And then if you do want a PDH, you can click that box again. We had over 1,000 registrants for this one. So this is hopefully going to be a great presentation for you all. I will quickly go into our summary. So we're going to do a quick introduction of how we're all connected, and then I'll pass it off to Ethan. Ethan Cargill is our VP of Conetec Group. He is a geotechnical engineer graduating with a bachelor's in civil engineering and a master of science in civil engineering focus in geotechnical from Georgia Institute of Technology. He holds professional engineering licenses in Virginia and South Carolina and is a board certified diplomat of geotechnical engineering. He's been there with Conetec for almost 20 years and is the vice president for the US group.
Hi, everybody.
So ultimately, we're all part of the Vinci group. Vinci does over $61 billion a year in turnover, and the contracting arm, which is a part of each of these different groups, does about 80% of that revenue. And then we're most closely connected through the Solitanche Fresnel group, which operates in 4 segments: the soils, structures, nuclear, and data solutions. We're all part of the soils group, where Nicholson Construction is under Solitanche Bashi, which is more structural elements in the ground. And then Menard is the group over Conetec, EarthTech, and Farrell, doing this testing, and then also more shallow foundations and those types of solutions. We're all sharing that culture of a global approach with local focus, technical expertise with our hyper specialization in geotechnical, and we have those collaborative solutions. So I will turn it over to you, Ethan. Carry it away.
All right, let me share my screen real quick. Can you see my presentation?
Not yet. It might be on a different.
Nope.
No?
Not yet, no.
Let's try this again. I guess I better hit the share button.
There you go.
So
So
we're seeing
your blue screen. So if you
All
can
right.
carry over your presentation there.
Perfect.
Boom.
How about now? There. All right, perfect.
We are in.
Well, thanks, Ryan and Frederic. It's certainly a pleasure to get the opportunity to present the subject to you folks. We're going to focus on kind of intro to cone penetration testing. I know a lot of you are familiar with it. And then we're going to kind of go into some advancement in site investigation methods that you may not be familiar with. But I know Ryan told you about our group of companies. I'd just like to take a quick opportunity to tell you about Conetec. We are a geotechnical and environmental site investigation firm. We're one of the largest in the world. We have about 500 people, over 500 people, and we operate out of 5 countries. You know, many people think when they think Conetec, they think only cone penetration testing. And that's not the case. We have experts and equipment to tackle just about every kind of site exploration method. So we're very versatile in what we do. So enough about Conetec. Let's get into the meat of the presentation. And I wanted to start out with this slide right here. For those of you that have seen maybe some of Paul Main's presentations, you'll recognize this slide. It's one of his slides. I like it because it shows all the contraptions and apparatuses out there to investigate what's under the ground. There's a lot of different choices you can make, and it's all based on what kind of answer or parameter you're looking for. For this presentation, we'll kind of start with the cone penetration test. So what is cone penetration testing? Cone penetration testing is pushing an electronic probe into the ground 2 centimeters a second. During that time, we measure tip resistance, pore pressure, and sleeve friction. We take those values after we're done with the sounding and plot it up in a CPT log. I'm sure many of you have seen one of these things. So y-axis is with depth. Let me get my pointer going here. Y-axis is depth. Here's our tip resistance. We call it QT. It's corrected tip resistance. Friction sleeve. Friction ratio is simply the ratio between sleeve and tip. And dynamic pore pressure. In this blue line here, we also plotted hydrostatic pore pressure. So we can take these values and correlate them to soil behavior type. Now, soil behavior type is just how it sounds. It's how the soil is behaving. It's not how the soil would classify with the USCS classification based on grain size. And so it's how the soil behaves when we do the test. And so you can see just a little refresher on reading these CPT logs. In the more coarse grained soils, the sands, typically we have a higher tip. And if it's freely draining, our dynamic pore pressures are pretty much hydrostatic pore pressures. In the finer grained soils, we have typically lower tip resistances, and we start building up pore pressure when we push our probe through these soils, and so we have elevated pore pressures here in the finer grain soils. So, really quickly after looking at this data, when you start first look at it, it just looks like a bunch of squiggly lines, but once you start thinking about it and maybe draw lines for layers, it's really easy to read these logs. And so in addition to these measurements, we can also do a number of other measurements. One of them is seismic measurements, either shear or compression waves. And the way we measure the shear and compression waves is we generate a shear or compression wave at the ground surface, and we measure that wave using a geophone in the cone and we measure that wave as it passes our cone. And we do this at several depths. And once we do that, we collect the data, we analyze it, we pick a common feature on the wave, and we can calculate velocities. And so we have a difference in ray path length of the wave, travel path of the wave, and we have a difference in time. And so distance over time, we can calculate velocities, both compression and shear wave. One of the biggest, I guess most popular uses people use with shear wave velocity data is simply seismic site classification based on the IBC. We do a lot of seismic calls just for that. For a more complex problem, when you really want to evaluate the stiffness of the soil, because you have maybe you're designing a machine vibration foundation, or you're designing for earthquakes and things like that, then you'd want the maximum shear modulus, which is simply the mass density times the shear wave velocity squared. And that parameter is used in a lot of that design. It also can tell you if your soils have a potential to liquefy. Again, it goes back to stiffness. We want to look at some data. Here, the graph on the left is shear waves plotted. Again, y-axis equals depth, x-axis equals time. So you can see a shear wave kind of travels horizontally like this. And so as our cone gets deeper and deeper in the ground, it takes longer and longer for that shear wave to arrive and pass our cone. And so we can take a common feature on each one of these waves, compare the time difference, and calculate the shear wave velocity. On this right side graph, this is compression waves, and you see it travels as a compression wave. Again, we can pick a common feature on each one of these traces and calculate our compression wave velocity. You'll notice a big inflection point here. And if you calculate the velocity for these, that's 400 meters a second versus 1500 meters a second. Typically, when a compression wave encounters fully saturated soil, the predominant wave speed going through there is governed by the water in the soil, and the wave speed of water is 1500 meters per second. You can also see that since we hit a high impedance zone here at the water table, we have a lot of energy reflecting back up through the profile, and the wave amplitudes are significantly diminished on this. So it can become very difficult to interpret compression wave velocity data below the water table, especially if it's 100% saturated. Another parameter we can measure with a CPT, we can stop and do a pore pressure dissipation test. And so that's simply stopping the cone and monitoring the dynamic pore pressures with time. If we let the test go out forever or long enough, we'll eventually reach the equilibrium pore pressure value. But we can also calculate horizontal coefficient of consolidation. And we do that by, here's some typical dissipation tests. We do that by looking at the time it takes to get to 50% dissipation, and we call that the T50. Tay and Holsby did some work on this, and they developed a correlation from T50 to horizontal coefficient of consolidation with this chart here. And you get a C sub H value, or you could simply plug it into this formula that they also provided to get it. And so IR is rigidity index. This is diameter of cone. And so you'll notice this looks like suspiciously like Terzagh's one-dimensional consolidation theory equation, just with a minor tweak on it. And that's what they based it off of. So, I'm not gonna, here's some more data. There's not much to say about it except, wow, it's 165 meters, which is pretty deep. I use this plot in here just to illustrate that cone penetration testing is not just for shallow explorations. Depending on the soils, we can go as deep as, as 165 meters or better. You got to have the right soil conditions to do this. This one, we hit a bit of a snag and we had to drill out for a few feet, but yeah, went right down and got it. So some of the applications that we do with this data, certainly stratigraphy. And if I go back to the last plot, you can see that we really get fine detail on the layering. And then also groundwater conditions by doing pore pressure dissipation testing. The top three in geotechnical design is stress history, strength, and compressibility. Certainly strength and stress history, great correlations with CPT. If we want to get time rate of consolidation, we can do a pore pressure dissipation test and get a coefficient consolidation value. We can also directly calculate liquefaction potential, both cyclic and static. And that's a real popular use for CPT data. We have direct and indirect design methods for deep and shallow foundations. And so what I mean by direct is that we can plug the CPT data directly into a method and it, we'll get out pile capacities like LCPC is a method, Unicone's a method. They'll both give you deep foundation design capacities just from CPT data. An indirect design method would be where we take our CPT data and we correlate it either to an undrained shear strength or a friction angle, and then use maybe the alpha method or the beta method to calculate foundation capacity. So we can hit it from two different directions, and hopefully, the results agree with each other. The CPT is limited to soil. You can't push through rock, but we got some pretty big rigs. There's rigs up to 35 tons out there or more, and under the right conditions can penetrate through some very, very hard soils. And it's applicable mostly for soils, small gravel and grain size and below. So looking at the data again, here's another way to present it. Here's normalized tip resistance. So we take the tip resistance and normalize it with overburden pressure. And this is especially important as you look at deep data. You know, the tip resistance is a function of the soil strength and the stress conditions. And so as you get deeper and deeper and deeper, the stress conditions play a much higher role in your tip resistance than maybe the soil strength does. And so that's why we normalize it with overburden to look at the data a lot of times. Here's our dynamic pour pressure. You can see at each one of these blue triangles, we do a dissipation test to equilibrium, and these blue circles are the value. And so we define the line, equilibrium line. This looks hydrostatic here, but if we were on a dam or an embankment, we could have non-hydrostatic conditions where pour pressures drop, some with depth, and yeah, and wouldn't be a straight line. There's a number of parameters we can plot up. I picked out a few here. One's the cone index, I sub C. More and more correlations, modern correlations these days, use this parameter as one of the parameters in their equations. Here's undrained shear strength, looked at a couple ways. If this profile was more sands, we'd plot friction angle here. Over consolidation ratio or yield stress ratio, however you want to call it. There's a number of correlations for that. Paul Main has some interesting observations when looking at different OCR correlations in determining either sensitivity or organic content and things like that in the clays. And so he's got some neat data sets to look at that. We can even calculate N160 if that's what makes you comfortable. And so it's you know, just a correlation. And of course, we have the shear wave velocity data. And in that, we calculate the VS30. This is for the IBC seismic site classification. So it's the average, well, or it's calculated over the top 30 meters based on the times. So applications for the data is pretty much anything that you build on soil or with soil. The CPT is widely accepted in using. Buildings, bridges, dams, embankments, retaining walls, anything that you know, deals with the soil. The CPT has become more and more widely accepted as the go-to tool for those things. For those of you not that familiar with CPT, there's a lot of advantages for it. It's relatively fast. Penetration rate is 2 centimeters a second, and so for every meter, it takes 50 seconds to push a meter, and so that's relatively fast. It can be economic. If you have enough data, you know, enough deep soundings out there, cost per meter for CPT can be significantly less than the cost per meter for drilling. Now, if you just get a big CPT rig out there to do one hole for you, it's going to be pretty comparable. But because the CPT rigs are so efficient and fast, when you have a lot of deep data, you really are, you know, really are efficient, and the costs go down. It gives you a continuous profile, which compared to the SPT, where you usually take a sample every 5 feet, you get readings every 1 to 2 centimeters in the CPT, or maybe even less. If the CPT operator or contractor performs a test in accordance with ASTM or ISO standards, the test is proved to be very repeatable and accurate. As long as you abide by those standards, you should get very repeatable and accurate data. It's easy to add shear wave velocity and compression wave velocity measurements and other sensors we can talk about later on in the presentation. And one of the biggest, things in geotechnical design is knowing your effective stress conditions. So if you do some pore pressure dissipation tests and get the equilibrium pore pressures with depth, you'll know the pore pressure conditions, and you can calculate your effective stresses. And it is an in situ test. We're not pulling a sample out of the ground and taking it to a lab with possible disturbance. The test is invasive, but it does test the soils in their natural state. A bit of history on the CPT. It was developed by the Dutch in the 1930s. In the 50s and 60s and 70s, we added friction sleeves and piezometers and electronic recording devices. In the 80s and 90s, even up to 2020, Paul Main and Peter Robertson have been very active in doing research to advance this industry. They've done a lot for CPT testing, and they're widely recognized as experts in the field. And we get to the 2020s now. We're looking at automation, machine learning, multi-module. We got cones going out on Mars rovers. It's come a long way in its history. If we wanted to compare that to other tests, standard SPT set testing developed in the 1900s, cone penetration in the 1930s, and you look at those two things and say, well, CPT is just about as old as SPT, but when you put it in the context of comparing a Dutch cone from the 1930s to a seismic piezo cone in 2023, if you look at a standard penetration test and look how they did it in 1900 versus how they do it now, there has been a couple advances in energy measurements and hammer design, but essentially it's just about the same test. And so when you see the 1930s for CPT testing, that's a very modern test these days. Vein shear testing has had a similar evolution. It was first developed in the 1940s. Now we have electronic veins with downhole load cells and everything like that. In the 50s, Louis Menard developed the pressure meter. Sonic drilling in the 70s, and in the late 70s and early 80s, Silvano Marchetti developed the dilatometer. And so what I'd like to talk about next is kind of things that came after these things that maybe you're not as familiar with the traditional tests. So the first thing we'll talk about is add-on modules. What I mean by add-on module, you still have the standard CPT here, but we add on a module behind it to measure additional parameters. And some things we can measure is resistivity or soil conductivity, ultraviolet induced fluorescence. If you haven't heard of that, it's an environmental tool. And if a petroleum hydrocarbon is exposed to ultraviolet light, it fluoresces, and we can measure that fluorescence and determine if we got contamination in the ground. Geoprobe developed a tool called the membrane interface probe. It's a very good tool, widely used. It consists of a heater block with a membrane here. And so the heater block volatilizes the compounds in the ground. A carrier gas, they go through the membrane, a carrier gas takes it up whole to a GC, and you can speciate the contamination. Very popular tool in the environmental world. Geoprobe also developed the hydraulic profiling tool. Basically, you inject water into the soil at a given, and based on the pressure and volume measurements, you can determine, estimate permeability of the soil. We do a lot of testing, gamut testing in mine tailings and in other sites where they're interested in the clay content, or they're interested in if there's any radioactive material in the ground. And so basically, it's just almost like a Geiger counter down the hole. I know that's probably a bit simplistic, but yeah, we can detect the radiation downhole. If you want to see the soil sample, we have downhole cameras. Basically, you have a port on a module with a lens, and we can either take video or high resolution still pictures. There's been a lot of work being done that take these high resolution images and does image analysis on it, and they're trying to infer things about the soil, such as grain size, distribution, and things like that. We also, I don't know if you've heard of full flow penetration testing. It's not an add-on module in the back. We actually replace the conical tip with a tip of much greater projected area. It's either a T-bar or a ball. A T-bar is just a horizontal ball, a bar, and a ball is just how it sounds, a ball. We'll talk about that next, full flow penetrometer testing. It was developed by the University of Western Australia in the 90s for the offshore industry. And so in the offshore industry, you have very deep water, so very high pressures, and you have soft sediments. And so they found if they use a conventional CPT, they weren't getting very good strength estimations. And I kind of alluded to this earlier in the slide. The tip resistance you measure with a CPT is a function of in situ soil strength and pressures. So overburden can influence up to 90% of the tip resistance. And so the actual strength of what you care about plays a small part in the values you measure in tip resistance with a conventional cone. So the theory behind the test is the geometry of the tip will significantly decrease the correction for overburden pressure. So how does that do that? Just looking at the test mechanism, we push the probe in the ground, the soil flows around the probe. And I should have mentioned this at the beginning. In order for this test to work, the soil has to be soft enough to flow around the probe. And so it has to cover the probe. And when it does that, a lot of the pressures acting on the tip are canceled out by pressures acting on the backside of the tip. And so the pressure that you see affects the tip resistance turns out to be only the pressure in the shadow of this shaft. And to say that another way, we look at our strength calculations for CPT or ball or T-bar testing. It's Q net over N is our undrained shear strength. To calculate Q net for CPT, we use this equation right here, and you can see here is the total vertical stress factor. So if this is big, you subtract it from this, and it becomes it could be the strength could be a very small part of the test. With full flow testing, we still have the total vertical stress, but we reduce it by the ratio of the area of the shaft over the projected area of the tip. And so if the projected area of our tip was 100 centimeters squared and the projected area of our shaft was 10 square centimeters squared, we reduced the overburden effect by 90%. So significant reductions. And it's been found that this provides a very superior estimation of soil strength in very, very soft soils. Soil soft enough to flow around the probe. Here are some results. And we plotted up vein shear testing with it, and you see that there's very good agreement. The one thing that I'd like to point out about this plot is how low the strengths are. I mean, you're talking 1 to 2 kPa, very, very low strengths. We can also do some other things with the ball. We can, I apologize for the quality of this plot. It's basically comparing a ball and a T-bar, and it shows that, yeah, you get very similar results between bar and T-bar. But during this testing, we stopped the probe and then we cycled it up and down for a meter. And when we do that, we watch the degradation of the tip resistance. And once it gets to a steady state, then we know the remolded strength of the soil is the primary driver of this tip resistance. And so we can tell a lot about the sensitivity of the soil by cycling this ball up and down. If you wanted to, you can also measure on the retract. There's not too much use for doing that, but for this one we did. We wanted to just take as much data as we could. And so that's full flow testing. You'll see that. You may run into it a lot when you're investigating like dredge bowl areas or soft marine sediments. We've done it in ash, mine tailings, anywhere that you got really soft soils. Excuse me. So we'll go on to the next subject. So as Ryan said, this April I'll be with Conetec 20 years. Before that, I was a consulting engineer and very intimate with in situ testing and designing with in situ test data. And before that, at school at Georgia Tech, I did my master's thesis on cone penetration testing. So I've been around cone penetration for a long time. And one of the most common complaints about cone penetration testing is, one, you can't see the soil. And two, you might hit a hard layer that you refuse on and not get to the depth you need. And so by combining CPT and sonic, we try to end those concerns. And just, I'm not sure how many are familiar with sonic drilling, but it'll give you a very rapid and continuous core. For those of you who have seen a sonic rig in action, it's shocking at the beginning how quickly that can put steel in the ground. Typically used for instrument installation, well installation, getting through cobbles, and really it gets through some really bony stuff. Explore down deep. And so what we do, and others have done it also, you modify your sonic rig to accept the CPT ram set here. And so we push the CPT just like a conventional CPT. It pushes at 20 tons, just like a conventional CPT rig. Once you get to your termination depth, you can pull the CPT out of the ground and just run down right in the same hole, sonic rods, to get a soil sample. You can also offset if you'd like, but if you just want to look at the soil, you can do it down the same hole. Another advantage is if we encounter a refusal layer, we got the drill rig right there. And so the sonic will blow through the refusal layer, and we'll go back down with our CPT and continue the sounding of the termination date. So that's sonic CPT. The next thing I'd like to introduce to some of you, maybe many of you already heard of this, is variable rate CPT testing. And so at the beginning of the presentation, we talked about the CPT is pushing the ground at 2 centimeters a second. And so why would we want to vary the penetration rate for a CPT? So we know that many soil types undergo partial drainage at a push rate of 2 centimeters a second. If we were to be testing a clay, we'd be pretty confident that the conditions around our CPT test would be undrained during the testing. If we were testing a clean sand, we'd be pretty confident that the conditions were undrained, and we could see that in our dynamic pore pressure. And so those are, vanilla clays and sands. So what about all the soils in between? Well, they undergo partial drainage, and we refer to them as intermediate soils. They're typically low plasticity clays to silty sands. And if we want to take the data that we collect in these soils and apply a drain correlation or an undrained correlation, that could be questionable. So we want to look at the effective rate, penetration rate on our CPT measurements. And there have been a lot of studies out there. This one is from Jaeger in 2012. This was done in a centrifuge. Penetration rates varied from 0.002 to 20 centimeters a second. And if we look at the data, we can see that several of the tests step down in speed as they penetrated into the ground. And so if we just look at the slowest speed right here, millimeters per second, we can see that our tip resistances are significantly higher than the slower speeds. And then the pore pressures are significantly lower than the slower speeds. And so if we look at this 3 millimeter a second push, tip resistance are significantly lower, pore pressures are significantly higher. And so as we increase speed, tip resistances decrease, pore pressures increase. And you can see on this pink line, we almost got completely drained conditions for it if it had hit this hydrostatic line. So it shows you how much drainage conditions can affect your CPT measurements. And so, like I said, there's been a lot of studies going on about this. One thing I'd like to introduce you to is normalized velocity. That's simply the penetration rate times the cone diameter divided by the horizontal coefficient of consolidation. It allows us to compare data pushed at different rates with different horizontal coefficients of consolidation. And there's been several studies that come up with parameters where you have fully drained and fully undrained conditions. To look at it graphically, DeYoung summarized some results from studies going back to 2004 and plotted it here. So x-axis is normalized velocity. Y-axis is either change of pore pressure or a difference in tip or corrected tip. And so you see here at very low normalized velocities, we have drain conditions going on. At very high normalized velocities, we have undrained conditions going on. And anywhere in between, we have partially drained conditions going on. And so every soil, so that he developed a backbone curve based on these studies here. Every soil is going to have a different shape to this curve. And it looks like these studies are, a lot of them are kaolin and sand mixtures, I'm imagining. But yeah, there's been a study by Deansman on gold mine tailings, which has a significantly different shape to their curve than this right here. So, but for this curve, he picked a typical curve, a trend going through the data, and he developed, Jason developed a field decision chart for this. And you can use this, you can have it on the rig with you. And at the very least, you can just see where you're at when you're pushing a standard rate of 2 centimeters a second. So if I do a dissipation test and my horizontal coefficient of consolidation comes up to 1 centimeter squared per second, I know that I'm going to be in the partially drained portion. And so if I wanted to slow it down to get in the drain portion, I'd have to slow my push rate down to 0.01, 0.02, 0.03 centimeters a second. If I want to speed my penetration right up to get in the drained, undrained portion, I'd have to speed it up to about 10 centimeters a second. And so it's a good sanity check. Again, this is not going to be accurate for all soils, but it'll be pretty close. If you wanted to accurate for all soils, you'd have to take that soil, vary the rate of penetration, build your own backbone curve, and then do a chart like this. So here's some example data. This is from the Eastern United States. And so we pushed 2 centimeters a second until a couple depths here, one at about 8.8 and 14 meters, where we started slowing down the penetration. And so I'm going to focus on the data down here, and I'm going to zoom in, and I apologize for the graininess of it. So basically the black line is 2 centimeters a second. We stop the cone and we let the pore pressures partially dissipate. We don't let them dissipate all the way. And then we start pushing the cone at 0.01 centimeters a second. You can see we get an increase in tip resistance. Our pore pressures compared, this is 2 centimeters second pore pressures. Our pore pressures are much lower also. As we speed the test up, our tip resistances get more and more in line with the undrained conditions at 2 centimeters a second. And our pore pressures arise. So then what we did, we pushed it 0.5 and, seen it's very similar results to 2 centimeters a second. We stopped the cone, we left it in the ground overnight and let the pore pressures dissipate entirely. And what we did the same thing. We started it at 0.01 centimeters a second, much higher tip resistance. The pore pressure was lower. As we increased the speed, tip resistance dropped, pore pressure increased. You can tell that our pore pressure values still not the hydrostatic. This is the hydrostatic line that you just kind of extend down here. And so in this test, we did not become drained, even at the slow speed. I think we probably have to drop our speed down to either 0.001 or drop it down 1 or 2 orders of magnitude. Hopefully 1 order of magnitude would do it. So some of the limitations for variable rate CPT testing, soil variability is the biggest challenge. If you're comparing data at different penetration rates, you gotta be convinced that the soils are similar that you're testing in. Otherwise, you can't make the comparisons. You need specialized equipment. Typical CPT rig is not going to be able to push to speeds down to the lower range accurately. And so you'll have to do some modifications to CPT rigs. In long test times, if you're going 0.1 centimeter a second, it's going to take you 1,000 seconds to go a meter, over 10 minutes. If you're pushing 0.01, it's going to take 10,000 seconds. So the test times can get extremely long. Luckily, you don't have to go that big of a distance. There's studies out there, and some of them say you only have to go, 4 to 6 cone diameters in distance to get meaningful results. So regardless, though, even those short distances can be very long test times. Getting a little bit away from CPT testing, a related side note is fast vein testing. And so we can use our logic with variable rate CPT and apply it to vein testing. And so the standard ASTM test rate rotation rate is 0.05 to 0.2 degrees per second. Pretty slow. And so to calculate undrained shear strength, we take the failure surface, so around the cylinder, top and bottom, and we apply this torque around it that we measure during our test. To calculate undrained shear strength, we integrate this torque over this area and get the undrained shear strength. For this equation to be valid, it has to be undrained conditions in these shear zones. And if we're in a clay, in most clays, we're pretty confident, yeah, we got undrained conditions going on and everything's good. But the problem gets to be when we, start adding silt content, or we're like a mine tailing or ash deposit, where we might have partial drainage occurring during the test. And so what we want to do is we want to speed up the rotation rate to make sure we have undrained conditions along that shear zone. And we can do it up to 30 degrees per second, which is pretty fast. And so you don't want to do it this fast if you don't have to, because the faster you go, you start seeing viscous effects and things like that. And so there's a lot of studies out there. Well, I say a lot, I think there's 3 or 4 studies out there on how to calculate the correct rate that you should rotate the vein to ensure undrained conditions in your particular soil. And they're all based on horizontal coefficient of consolidation that we measure with a CPT, pore pressure dissipation test. And so again, horizontal coefficient consolidation, there's a lot of uses for it. And so you'd want to just calculate it up and just do it at the minimum rotation rate where you're sure that you're getting undrained conditions. Okay, our next one, and I hope I'm not running through these too fast. I wanted to cover introduce a lot of things, and I'm not providing a lot of detail on these, I realize. So our next test method I'd like to talk about is nuclear magnetic resonance. It's an NMR probe like this. This one's a Vista Clara probe. You can either deploy it with direct push methods, a PV cased hole, or an open hole. The NMR uses a powerful electromagnet to transmit pulses that excite hydrogen atoms, and then we measure the response. The NMR signal is generated and detected only within a thin cylindrical kind of shell surrounding the probe. And so you want to make sure that your shell, where you're measuring things at, are out of the disturb zone of your probe. So the probe will measure the initial amplitude and subsequent decay of the returning induced magnetic field. And the initial amplitude directly indicates the quantity of hydrogen containing fluid in the formation, which is your volumetric water content in water-bearing soils. The decay, if we look at the decay, the rate of decay, we can tell a lot about the pore size. And this is probably a little too basic in my explanation, but basically you got a bunch of excited hydrogen particles here. And in larger pore sizes, when hydrogen particles are bouncing off the walls of the soil grains, that's when they lose energy. In larger pore sizes, it takes longer for them to lose their energy, to decay. And because there's not a lot of surface area around here. In really small pores, it decays really fast. And so there's correlations out there to tell pore size by decay time. Now most soils have heterogeneous pore sizes. They got small, land, large, and all that. And so there's methods with the data where you can determine, all right, which water is bound in like a silt or a clay, and how much water is mobile, like in a clean sand. And they can tell that. And you also know they can estimate hydraulic conductivity with this. So let's look at some example data. So we get volumetric water content with depth. And so we know we're saturated in this zone here. So if we know we're completely saturated and we know the volumetric water content, we know that all the pores are filled with water, so we can tell the porosity. Once we know the porosity, we can calculate the void ratio. And for a long time, this has been kind of like the holy grail of in situ testing, and be able to measure void ratio accurately. And so this testing is showing a lot of promise. It's well established in the petroleum industry and some water well industry. But in the geotechnical industry, there's still a lot of studies going on to make sure it's applicable for what we do. I'd like to point out a technical breakthrough abstract currently by David Reed and Andy Fourier and others, talking about the potential applications for NMR testing. And so more to come on this. There's some very promising things out there for this, but we'll see. Lastly, I'm good on time. I'd like to talk about machine learning. And so we're going to get out of the field and come to the office and to look at machine learning. So machine learning is a subset of artificial intelligence. We all heard about it. It's in the news all the time these days. Very data hungry. It's applied to problems that are too complicated for us to figure out. And so the process of this is we collect the data, we prepare the data and split it into test sets, training sets, and validation tests. We train the model with the training set. We run the validation set through the model and test it and validate it. And we keep on adding more and more data to it. So there's a lot of geotechnical uses for machine learning, especially improving correlations. And so we've done some work looking at shear wave velocity. Here is shear wave velocity estimated versus measured for machine learning. Here it is estimated using a correlation developed by Main. And here it is estimated using a correlation developed by Robertson. You can see there's a lot of scatter in all of it, but there's less scatter in this one. And so the more data you put in this, the better the model becomes. and the correlations get better and better. We've also done this with unit weight. Here's one from Robertson Cabal, the correlation. Main, here's a machine learning. Again, see tighter data set, tighter correlation. And so there's a lot of promise for this also in the future. The one thing that you got to remember is the more data it has, the better the model becomes, but it has to be high quality data. If you put garbage data in it, you get garbage data out. And so if you're going to put your faith in an ML, a machine learned correlation, you better have faith that the data that went into that model is good data. And so that's it for me. I'd like to take one chance to point you in this direction. If you're interested more in cone penetration testing and parameters to get from it, we created a CPT design parameter manual with Paul Main. It's free to download at www.conetec.com. And yeah, everybody's welcome to do that. And that is it. How do you do on time, Frederick?
Oh, you're good. You're good.
All right.
Ryan, you're coming back?
I'm back. Thank you so much, Ethan. We really appreciate it. We did have a few questions come in. So we'll take some time here at the end to get a couple questions answered live. Won't try to give you all the hard ones, but there's some really good questions in there. A softball one to start from our retired chief engineer, Tom Richards. He's asking, there was a picture in your slides that showed the cone sleeves, and from his experience, there used to be a wire that had to go in the middle to transmit the data from the bottom of the hole. Is that still necessary, or is it passed through the casing now?
It's mostly necessary. There are technologies out there that use radio waves and light to transmit data. The most robust method still is the cable route. And so, yeah, I know what picture is he talking about. And yeah, I'm not sure why a cone cable wasn't in there. We use cone cables.
And for another one. So how does seismic CPT compare to the traditional down the hole shear wave testing with regard specifically to accuracy?
Well, so it should be very similar. And there's some studies out there that show how it's very similar. I mean, you still generate the shear wave at the ground surface, and you measure it with geophones down hole. And so, yeah, it's pretty similar.
Okay. Okay, from Tom Gallagher, how does CPT consolidation test results for clays and organics compare to laboratory consolidation tests, specifically with time and the amount of settlement?
So, three-part question sounds like. So organic content, Paul Main's done a lot of good work on identifying clays with higher organic content. And then I think if you just Google Paul Main and organic content, you can find that. And then as far as magnitude for consolidation tests, the magnitude of settlement, a consolidation settlement, the CPT is not very good for estimating magnitude of consolidation settlement. You can get a modulus and estimate magnitude of elastic settlement, but not consolidation settlement. As far as time rate, yeah, once you get a horizontal coefficient of consolidation with a pore pressure dissipation test, you can actually measure or calculate the time for consolidation.
Gotcha. Okay, there were a couple questions after the test has been completed with the hole left. How are we filling those typically? And then one specifically on the methods of backfilling the sounding hole when doing CPT in levees and dams.
Sure.
Have water.
Sure. So the short answer, it all depends. It all depends on the site, the local regulations, and the risk. And so if we just had a site, out in the middle of the country and in a farm field, typically we just pour bentonite chips down the hole. Now you got to remember, we don't pull any soil out of the hole. So most soils, this hole is going to close up, and the portion that doesn't, bentonite chips usually caps the top and keeps things from going down the hole. if the hole doesn't close up. For environmental sites or levees or dams where you do not want the risk for having a pathway is great. You don't want to gamble. And so we do typically trimming grouting. And so we'll pull the CPT out of the hole, run some grout rods down there with trimming rod and grout as we extract it. Or there are some methods that we use where we grout as we go down the hole and come back out the hole. Yeah, it all depends on the situation.
Very good to know. Here's another one that came through. So on one of the attachments, you had the ball attachment. Is there a specific S sub U range, PSF range of the soil that is able to be used in? And then does it affect the production rate of the CPT as well?
Yeah, it doesn't affect the production rate very much. I mean, you're still pushing it down at 2 centimeters a second. If you do some cycling, that could add some time. It's a combination of the overburden and the soil strength. And so if you push that ball in the ground and you look and you create a post hole, the soil is too stiff for that. And so, if they want to, a lot of people equate it to blow counts. I always tell them that, if you got weight of hammer or weight of rod or 1 or 2 blows per foot, ball might work. With CPT, if your tip resistances are, less than 0.1 to 0.3 megapascals, the ball should work. They just got to be soft. And if I could think of a consistency, like a really thick pudding or something like that, or maybe a little stiffer than that.
10-4. And kind of along the same lines, defining more significantly the refusal for CPT. How do you know where to stop before damaging the tip? I'm sure you know it very well, so you don't.
Well, that's not a perfect science because we have a lot of cones we break. But a good operator will be able to tell right before they break a cone. The obvious thing is rod rebound. Once they push down and they unclamp, if those rods spring back up a little bit, we know we're starting to put a bend in the cone rod string. Another very obvious one is we lift the rig off the ground. And so we exceed the push capacity of the rig. And so that's when we call refusal. Yeah.
Good.
And inclination, if inclination gets off, you can call refusal there too.
All right, I'm going to throw one more at you, and then we'll answer the rest after the fact. But this one's more about the data. So tip resistance is measured at approximately 2 centimeter intervals, providing a discrete data point every 2 centimeters. However, the sleeve is much longer than the 2 centimeters. Is the sleeve data point averaged across the length of the sleeve? Also, the sleeve is several inches behind the cone. Is that T-slip data offset so it matches?
Okay, so the sleeve, you're right, the sleeve is longer, but it acts on a single load cell. So we measure a single load for the length of sleeve. We apply that load to the mid height of the sleeve. And so we offset the data. We correct the sleeve data and drop it down to where the midpoint data of the sleeve data matches the tip data at that same depth. Yeah.
So the software does all that.
Mm-hmm.
Okay.
Yeah.
Interesting. All right, Ryan, we're good?
Good to go. So there are probably 20 more questions in there that we will take some time, Ethan and his team, to get some answers back to you on the more specific that we weren't able to answer during this time. But thank you all. Thank you, Conetec and Ethan, for your time and doing the presentation. And then a couple of reminders as we're logging off. There will be that log off survey. Be sure if you do want your PDH to make sure to fill that out and be on the lookout for the next 60 minutes with Nicholson. Thanks again.
Thank you, Ryan. Thank you, Ethan. That was great.
Thank you.
Thanks everybody. You guys can log off. I'll stay a few minutes to let people log out. Okay. Thank you, guys.
Thanks.